I want to take a few moments to talk about statistical background of the X-bar chart. Let's take the previous example. A fire department is concerned with its ambulance response times measured in minutes. The target average response time is 15 minutes. Each week, a sample of 3 observations is collected. So let's review some terms. First, we have a term called the population. The population consists of all the response times of all instances occurred at this fire department. And we have a term called the population mean. We're going to use mu to denote the population mean. The population mean is the average of all the values in the population. Is mu known to us? No, because mu is the average of all the values in the population, but here we are only sampling a few observations, so we can't compute mu. Mu is unknown. Next, we have a term called the population standard deviation. We use sigma to denote this quantity. It's the standard deviation of all the values in the sample, in the population. Is sigma known to us? No. To compute sigma, we need to compute the standard deviation of all the values in the population, but we are sampling a few of them, so we can't compute sigma. Sigma is unknown. Next, the sample size. N, it's the number of observations taken for each sample. So this is the data set we collected, and let's think about how the sample mean is computed. In the first sample, we compute the average of these. We get a value of sample mean. In the second sample, we compute the average of these. We get another value of the sample mean, and we repeat this. And these sample means are different from each other because we have different values in each sample. And if we keep doing this, we'll end up with a bunch of different values of the sample mean. And using those values, we can create the histogram. A histogram will look like this. On the x-axis, we have the range of all the possible values for the sample mean. And on the y-axis, we have the percent frequency. And it tells us what percentage of values are within each range. Now, and this shows you how the values of the sample mean are distributed. And next, I want to turn to a theory called the central limit theorem. The central limit theorem says something about the shape of this distribution and the mean of this distribution and the standard deviation of this distribution. First, it says the shape of this histogram gets close to a bell shape when the sample size n gets large. And this is true regardless of what type of data set you have. And next, it says the mean of this distribution gets close to the population mean when the sample size is large enough. And next, it says the standard deviation of this distribution gets close to sigma over the square root of n when the sample size is large enough. So in other words, when the sample size gets larger and larger, the histogram gets closer and closer to this bell curve with mean mu and standard deviation sigma over square root of n. Next, I want to turn to the empirical rule. The empirical rule says if you have a data set with a bell shape, then 99.7% of the values are within 3 standard deviations of the mean. So here is the mean minus 3 times the standard deviation. Here is the mean plus 3 times standard deviation. And if you have a distribution with a bell shape, then 99.7% of the values are within the range. Now, according to the central limit theorem, we know the standard deviation is sigma over the square root of n. So if you combine the two, we know that 99.7% of the sample values are within these two values. So we can say something like this: 99.7% of the sample values are within these two. Now, if you rotate this graph 90 degrees clockwise, then we'll have an ideal X-bar chart. This becomes this. This is the upper limit, mu plus 3 sigma over the square root of n, and this line becomes the lower control limit, mu minus 3 sigma over the square root of n. So this is the ideal X-bar chart, and we know that mu is unknown to us, and also sigma is unknown to us. So instead of these values, we're going to use some estimates of these. So instead of mu, we're going to use x double bar. X double bar is an estimate of mu. And instead of this, we're going to use A2 times R bar. This is an estimate of this. So this is the actual X bar chart. Now remember, 99.7% of the sample means are within the two limits, and only 3.3% of the time the sample means are outside the limits. And this happens even if the process is in control. In other words, there's nothing wrong in the process, but 0.3% of the time the sample mean is outside the limit, so we have to conclude that the process is out of control. And that's an incorrect decision. And that happens 0.3% of the time. So this is a risk associated with the control chart, and we are going to talk about this in the next part.